the guys tonight asked me to make sure they got every minute of their hour. They have been working on their presentation. They have practiced. They've rehearsed twice. Of course, we have Ron, WA6YOU, and Lee, KD4RE, and they're going to talk to us about antennas, which is one of those things that I always need to learn more about and relearn every time. And I know that for many of us who are in compromised locations with HOA restrictions or in townhomes are particularly in need of kind of what they're going to hear tonight. So they called it antennas again. And, you know, my response is, yeah, antennas always.
Welcome to Vienna Wireless tonight. I'm Ron Payne, WA6YOU. We have Lee Garlock here, KD4RE. We put together this presentation this week for people in the club, mainly the ones that have been moving into the high HOA areas, the ones that live in apartments, the ones that live in townhouses. And we have tried to make this pretty much simple. And we're only going to take about 40, I think we have 40 slides tonight. We'll have plenty of time at the end for questions. So with that in mind, I'm going to hand it over now to Lee, and I'll be jumping in every so often. So I'm going to go mute, and Lee, it's all yours.
Okay, so hopefully we're cooking through okay. Antennas again. So you can see here, antennas take all kinds of forms. There are little pictures. There's a double ridge horn down here on the lower left-hand corner. That's actually an antenna, believe it or not. Most of us are familiar with the Aggies. We'd love to have some up in our backyard to work DX with. And then there's a radio telescope. We can hear radio signals from Alpha Centauri or wherever. Here's our agenda real quick, what we're going to talk about. We're going to go over some basics of antenna theory for everyone. We're going to talk about the simple horizontal wire and the dipole type antenna. A vertical, small transmit loops, which are a good option for a lot of things, interference issues. I'm also going to touch on something about radiation safety, and we call it the hazards of electromagnetic radiation to personnel. And this is part of the FCC rules, and we'll get into that at the very end of the presentation. So what the heck's an antenna? Antenna is, in my terminology, and after I came up with this, I read it in a book. It's a transducer. It basically couples the radiated electromagnetic fields to or from a transmission system, receiver, or a transmitter. So we're very familiar with antennas that have a length of wire or a loop of wire. It also can be a flared end on a piece of waveguide, like a horn antenna, we call them. It could be slots cut along the side of a piece of waveguide, which is used for a lot of like navigation radars, maritime, ship radars quite often use that type of antenna. It could literally be a slot cut in a sheet of metal, which actually works the same as a piece of wire, like a dipole. There could be a planar conductive surface mounted over ground plane, such as a patch antenna, and you probably actually have one because it's in your cell phone. And there are some esoteric antennas that can use weird things like plasmas, stream of salt water, even a dielectric rod. And if you want to see a saltwater antenna in action, go to YouTube and put in saltwater antenna, and you can watch Dan Tam out at San Diego use a stream of salt water to talk to somebody on 2 meters. So I'll let that be homework you can go look up on YouTube. So we're only going to be talking about wire antennas. I'm not going to get anything else. And in particular, we're going to talk about standing wave antennas and not traveling wave antennas like a beverage. Beverage antennas are great for receiving, but not for transmitting. So we're looking at really things you can use for HF and primarily 6 meters. I got a couple rules here. Number one, the performance of our wire antenna is strictly determined by the current distribution on the wire. That is the amplitude and phase distribution in the wires. And really nothing else matters. That tells you everything. VSWR has absolutely nothing to do with the performance of your antenna per se. Okay, the antenna doesn't really care what the VSWR or VSWR is. However, it does affect the coupling of energy to and from the antenna for your transmission system. And also your transmitter, receiver, transceiver cares a lot about VSWR, but the antenna does not. The rule 3, any conductor near your antenna, including your house wiring, the surface of the ground near your antenna, the siding on your townhouse or apartment, are all part of the antenna system, and they all will affect your radiation pattern, the feed point impedance, the whole enchilada. And sometimes your coax and transmission system can be part of the antenna. Sometimes that's intended, like a Carolina Windham has a section of a transmission line it intentionally radiates from. But most of the time, you really don't want your transmission line and equipment to be part of the antenna. So let's talk real basics here about what is a radio wave and how do we model it. We think of radio waves as basically being composed of 2 fields, electric field, the E field, and a magnetic field, the H field. These are mutually orthogonal to one another in a traveling wave, the transverse electromagnetic wave, which is radiating energy. And you can see here the direction of propagation is at a right angle to both the E and H field. So it's mutually orthogonal in a mathematical term to the E and H field. Also notice that if you take your right hand, put it up, or let's see, lay it flat, and turn it upright, your fingers pointing up will be the E field, the palm will be the H field, and if you push the fingers towards your palm, your thumb sticks out in the direction of propagation. And we call that the right-hand rule. Okay? So let's define a few terms here I want to go over real quick. Antenna gain. Okay, antennas are passive devices. They really don't have gain like an amplifier. They don't add anything. However, what happens is, let me go back one. They're like a balloon. So there's a fixed volume, but as you squeeze it, it goes out in different directions. So the way we have gain is basically it radiates more power in one direction than another. The total power does not really change. If anything, we lose some. Ideally, if all the energy is radiated in the same, equally in all directions, we call it an isotropic antenna. So for a lossless antenna, the term gain is basically the same thing as directivity of the antenna. In ham radio, sometimes we see gain compared to a half-wave dipole rather than an isotropic source, and the difference is 2.5 dB. So dBi and dBd are 2 terms you'll see when we talk about antenna gain, and they're referenced to the 2 different sources, and the difference is 2.15 dB. Let's talk real quick polarization. Polarization is and we get into this on the 10 meter, are you vertically or horizontally polarized? If you're vertically polarized, your E field is basically normal to the surface of the Earth. That is, it's vertical, right? Horizontally polarized means basically your E field is horizontal or, parallel to the surface of the Earth. Okay? Got that? So let's talk about current distributions real quick. The radiated fields are general, as we mentioned before, are strictly a function of the current and everything around it on any conductors. All the modeling software we use for wire antennas, be it NEC, EasyNEC, 4NEC2, MANA, which is popular in the UK, are all based on the method of moments, all work by determining first the current on every segment of the wire that you're modeling, and then it computes the radiated fields, the feed point impedance, and all from the currents. So again, currents is what matters. And real quick, a little bit of physics. Maxwell's equations state that anytime we have a time-varying current on a wire, it will produce a radiating electric and magnetic fields. And that the conductor in the time-varying electric and magnetic field will have a current induced on it based on the alignment of the conductor with the fields. Basically a receive antenna. So let's talk a little bit about elementary antennas. There's two kind of wire antenna, elementary wire antennas, okay? We have dipoles and we have loops. And these are the basis of your wire antennas. Both antennas actually have complex field structures around them. They have a field called 1 over, which falls off as 1 over d square or 1 over r square, the distance away from the antenna, which is called a reactive field. And we're going to show you that in just a second. Basically, this field does not actually radiate any energy, net energy, because it cancels itself out. But we need to consider them for safety purposes, particularly, as I said, the hazards to personnel. So let's take the basic wire dipole antenna. Okay, it has two E fields. One E field, which falls off as 1 over D, is basically parallel to the wire. The other E field is kind of radial outward from the wire. And the magnetic field, the H field, is kind of around our wire, here showed in the brown. So real quick, if you consider the two radial fields, you use our little right-hand rule, you'll see that the power radiated in one case goes up, the other one goes down. So the net result is 0. Whereas the field that's aligned with the wire, and you take your little thumb and hand and palm and line up your fields, basically has a power going out away from the wire. So a loop antenna works the opposite way. We actually have two H fields and one E field. So it's very much a similar deal. One field falls off as 1 over D, one of the H fields, the other is 1 over D squared, and we have an E field that falls off as 1 over D. The two fields that fall over as 1 over D are our radiating fields. The other one we don't care about except when we're dealing with the RADHAZ, and we'll get to that at the very end. So just remember that. Okay, let's talk about the simple dipole. Half wavelength piece of wire is an ideal dipole. It has a totally sinusoidal current distribution on the wire. And its radiation pattern and radiation resistance are really independent of where you feed the antenna. But the feed point impedance can change an awful lot. So in free space, if we have a center-fed antenna, the normal feed point impedance is about 72 plus J0 ohms. That is no reactance. That's what people call a resonant antenna by many definitions. And if the wire is located, we get it in a real world sense above the earth, then the ground's going to intersect the pattern. It's also going to affect our feed point impedance. And typically, that feed point impedance is going to be less than 72 ohms. And we may have a bit of reactance because the wire becomes in proximity to the earth and induces currents in the earth, and all that affects your antenna performance. Okay? End-fed antennas are kind of popular. I know a number of club members are using those. Well, the issue about an end-fed antenna is you're feeding it at the end where you have a high voltage. We'll show you that in just a second on the next slide, and a low current point. So our feed point impedance is rather high, like 3,000 to 4,000 ohms. So matching that to your rig requires you're not going to be able to use the internal tuner in your radio to match an end-fed antenna. Basically, you need some sort of a transformer or tuning network. And let's talk about the Wyndham's, another interesting antenna. It's fed about 1/3 the way from one end, and that gives us a feed point impedance somewhere around 400 ohms, plus or minus 100 or so. And they're kind of popular for one reason, and that is that on the harmonic frequencies, as you go up, the current and voltage distribution is such that you basically have about the same 400 ohms. So therefore, with a simple impedance matching, broadband impedance matching network like an auto transformer that's used in antennas like the Carolina Wyndham, you can actually match the antenna on several different frequencies down to 50 ohms without really having to do any tuning. Okay, so here's a half wave. Basically, real quick, okay, quarter wave sectors, 2 quarter wave sections tied to your transmission cable. Here's our current distribution. It's maximum in the center and minimal on the ends, okay? here's our voltage distribution. It's, again, very high. And as we mentioned, when we have an end-fed antenna, we have a very high voltage, very low current, so we have a very high impedance at the end. So this is kind of just a quick, simple representation of how the current, the voltage, and the impedance vary. And as I said, the feed point impedance anywhere along this half-wave wire is strictly determined by this ratio of your current and voltage at that point. The actual current distribution is not going to change for the half wave, okay, as you change the feed point. That's not true of other length antenna, but it is true for the half wavelength. So does a wire have to be a half a wavelength long? The answer is no. It doesn't have to be a resonant. It doesn't have to be a multiple of quarter wavelengths. It doesn't have to be a half wavelength, okay? However, the currents on the wire are not the same as the half wave dipole, and the pattern is not going to be the same. And in general, if the antenna is short relative to a half wave, you're going to have a very low radiation resistance. You're going to have a fairly low feed point resistance, and you're going to have a very high reactance at the feed point, which basically means it's a challenge to match them at 50 ohms, and that also they have a lower radiation resistance, and that lowers the efficiency of the antenna. In reality, do you really have an antenna issue? Not so much. You really have a coupler tuner issue with a single random wire. If you have a good tuning network, you can probably load into it. So it's something that you actually can use pretty much with anything, but don't expect to be able to hook a piece of coax to it and use the built-in tuner in your ICOM 7300, because that's not going to cut it in most cases. Okay? So what can we do? We can run a wire out your bathroom window, bedroom window, back of the deck, porch, to some tree out back and get on the air just with a simple horizontal wire antenna. Thin black wire makes kind of an invisible antenna. I had one in my apartment many, many years ago when I lived in Annapolis. It's very easy to implement an end-fed compared to a dipole. And as I said, the challenge is feeding it. And you got to be careful. You want to avoid, again, having your equipment become part of the antenna. And a question for people, have you ever been bitten by RF by the microphone? I think quite a few of us have. So we need to work on getting this thing to keep the RF currents off of your equipment and off the transmission line. And basically, so the key is really to have a good tuner, coupler, transformer to match your end-fed antenna. So I did a little experiment. I took a 32-foot length of wire, 3 feet off the ground, and I'm going to show you what the patterns look like at different frequencies and our feed point impedance, okay? So bear with me. So the red you see is the horizontal pattern. The blue is the vertical pattern of the antenna. So this is on 80 meters with a very short wire. So the pattern actually isn't too bad. Most of the energy is going up at a high angle, not good for DX, but hey, if you want to work the local traffic net and talk to people within a couple 100 miles, it actually is a pretty good antenna, pattern-wise. The problem is we get our feed point impedance. So you look here, our feed point impedance is between like 3 and 4 ohms, the real part of it, and the reactance is around capacitive minus J3000. So it's a little bit of a challenge to tune it. You're going to have a pretty high voltage, even with 100 watts at that feed point, because, again, you have a very high reactive load, very low resistance. So it's a very, very high impedance we're dealing with. Okay? This is with a dipole. So let's end-feed this same, let's end-feed the same antenna. Okay, we get the same pattern pretty much, but notice what happens to my feed point impedance here. My reactive component on the end-fed is really going through the roof. It's over 10,000 ohms. So again, this is going to be a real challenge to feed this antenna on this low, this end-feed this antenna at this low frequency. It can be done, and you can probably get out with it and work some local stations, but it's going to take a little bit of a challenge to do that. So let's try 40 meters. Okay, here's the dipole. So our whole length is a quarter wave, not a half wave. It's not too bad. We got some pretty good gain. It's, again, at a high angle, but it's still good for NVIS. You can talk to people within a couple hundred miles easily. Well, let's come over here to our feed point impedance. Well, again, it's a little bit better. It's up around, 12, 15 ohms. And our reactance is not quite as bad. It's minus J 1200 or so. So, again, it's becoming a practical antenna. You can probably build a matching network, and we can probably match this thing to get you on 40 meters with just this short piece of 32-foot wire. And this is my dipole. So let me go up to the end fed again. Hold on. So if you end feed it, again, we get the same pattern pretty much. But again, look at what happened to my impedance here. So I'm up a little bit better. I'm up about, 17, 18 ohms. But again, I'm dealing with about minus 10,000 reactives. So we still have a lot of reactance on the end fed. It is doable to use it, but the real issue is designing a matching network that will take this extremely high reactive load down to 50 ohms. So let's try 20 meters. Okay, so now this is getting close to being a regular dipole. You see a kind of a dipole pattern here in the red. Our elevation pattern has improved quite a bit. We got most of our energy is going off at lower angles where it's better for DX. And I'm not quite resonant because my antenna length here is a little bit short, I guess. Because my resonant point is at a little bit higher frequency, probably like 15 megahertz. But you can see here, we're not doing too bad. We've got about 67 ohms minus J, 80, 100. This antenna you can probably tune with the built-in tuner on your ICOM 7300 or whatever. It's not that far away from 50 ohms. Now, if I end feed it, again, the pattern looks pretty decent, as we would expect. It's actually the exact same pattern we had before. Look, before, after. There's no difference in the pattern, okay, as we were saying earlier. And this is the end-fed version. And again, okay, as we would expect, we're about 1,000 ohms real part resistance and about minus 5,000 ohms reactive capacitive. So how do we feed this? Well, typically what we do is we actually use a transformer, the 49-to-1 or a 64-to-1 ratio transformer to get that high impedance down to something 50 ohms. So, you can feed these high impedance antennas with the balun core. Again, the ones that really have really high reactance we got to be careful of because of the voltage on the ends of these antennas, unless we're running QRP. But even 100 watts, you got to be careful about making sure you don't arc over your matching network. So also I tried this on 15 meters. Looks pretty good, except because of our height above ground, you can see in my elevation pattern, now I've got more energy going higher up. And this is with the dipole version rather than the end-fed, but our feed point impedance here is about 280 ohms plus, in this case, inductive reactance rather than capacitors. It's about plus J900. So again, this is probably can be matched reasonably easily, and it actually would probably radiate pretty well. And then I'm going to end feed the same wire down instead of being center fed. You can see my pattern's got a little bit more distortion in it, but it's still not that bad. It's pretty good, actually. Interesting enough, my feed point impedance, hey, I'm right at 50 ohms, but again, I got a lot of reactance in here. Again, we went over the curve, and now we're capacitive reactance again. And you can see again about minus 4,000 ohms. And if I end feed the same antenna, got some interesting well, I'm ahead of myself here. Hold on. That was 15 meters, right? That was the dipole. This is the end fed. So let's go to 10 meters. What can I do on 10 meters? As a 10 meter dipole, I'm actually looking at two wavelengths. So I actually have two. If I'm feeding it in the center, I'm actually feeding it between the two ends of the like two dipoles back to back. So I get actually a good pattern. You can see here there's quite a bit of gain in it of the dipole. Unfortunately, because of the height issue above ground, which primarily determines our elevation pattern, we got a lot of energy going at a high angle, which is not so great. But hey, I'm actually resonant around 28.9. My reactance is 0. But my feed point impedance, because I'm feeding it right at the ends of like two one wavelength antennas, okay, so I'm at a high point. So I got like 4,000 ohms, actually 4,400 ohms or whatever, of resistive feed point. So again, we need to use a step down transformer, like the 49-to-1, or to bring this thing down to where we could use it. And let me go on one more here. We'll do our end fed the same antenna. We have much different current distribution. Notice what happens to our pattern. We actually now have a deep null, basically parallel to our antenna. Because we're having, this is a phasing issue because we actually have two antennas, if you want to think of those terms, and the way we're phasing them, we get this cloverleaf pattern because the way the current distribution is working with our end fed. And again, if we go try to match this guy, hey, it's up there, you know, as you can see on the left-hand side, you know, somewhere between 300 and 500 ohms. And our reactance, again, is fairly high, capacitive, about minus 2,000 ohms. So the reason I did this is just to give you an idea of what you can expect off a fairly short, you know, length antenna that maybe you could string between a window or the balcony and a tree in your backyard. And fed it. So you can see it all radiates in some cases where it's really short, not so well, but you can get out with it. The real issue is how do we match it? So let's talk about verticals. A vertical antenna is, of course, going to be vertical, so it's going to be vertically polarized. Most of the commercial ones you buy and you see advertised are half wavelength antennas, particularly those that claim that they don't require any radials. For multiband operation, typically they have traps in them, like say the R5, R7s verticals, for example, a lot of them. Typically they actually have one, or in a lot of cases, two different matching transformers in the base to bring that high impedance for the half wave of a couple thousand ohms down to 50 ohms. I know my R5 has two transformers. I know the R7 actually uses two transformers to bring the impedance down. You also can center feed a vertical, run the coax up, you know, through a pole and run another piece of wire up if you want. We hear a lot about quarter wave antennas. A quarter wave vertical basically relies on using the earth, the radials, as an image. If we had the antenna over perfect ground, the feed point would be about 36 ohms. Typically, it's going to be higher than that because of losses in the ground. And I go a quick story on that one. Many, many years ago, when I was still working in broadcasting, I was talking to a guy who had built this wonderful antenna on 80 meters, and he had all these radials, and he was complaining his VISWAR was too high. So he was cutting his radials to make his VISWAR better to raise the feed point impedance, but what he was doing was just adding additional loss into his ground. So the antenna was working worse and worse, but his VISWAR was getting better and better. So do not rely on VISWAR to tune your antenna, folks. Note here real quick, probably the best simple vertical is one that's 5/8 of a wavelength tall. This actually produces the best low angle radiation, the greatest inverse field, as we would call it in broadcasting. But its feed point's not going to be 50 ohms. But quite often you'll see, particularly for 2 meters and even 6 meters, 5/8 waves being advertised. So Ron's going to fill you in here on a little something. Okay. Yeah.
All right, this is the Outbacker Outreach, and the reason I want to show you guys, this is the picture on the bottom. It's like my mother's house in Vallejo, California, very strict HOAs. Nothing absolutely nothing can be put outside. Even your garage door, you can only have your garage door up when you're putting your car in, taking your car out, or cleaning your garage. Imagine that. This is California. This antenna is about 12 feet high, bust down to a couple of 4-foot sections. It comes with the optional base. You have to buy the base. And you notice I have the base sitting on the concrete where it shouldn't be. It should really be sitting on the lawn. Now, I've taken this out to Bull Run Park a couple times. It works fantastic through the entire HF spectrum. But comparing distances, like comparing signal strengths between Bull Run Park and Alabama and Bull Run Park in North Carolina is usually about 1 to 2 S units lower, 1 to 2 S units lower than an inverted V. But for you guys that can't put up an antenna, this is really a good viable option. Put something up, enjoy yourself, and then maybe take it down. Now, you see those houses in the back on the hill. I'm really surprised nobody called it in to complain about it. But this is the Outbacker Outreach, and if anybody wants to see one, I have one here that you can come over and check. But I do recommend buying the base with it also. In addition, for those of you living in apartments, I have used a Hustler Mobile Vertical on the balcony, my metal balcony. I used it as the ground plane. It worked very well. I put it at a 45-degree angle. I worked 138 countries during the sunspot high in 1979, 1980. And also I had a 10-meter whip, which was 8 foot 6 inches long. I would just go out there and screw it in at night and ham, and then in the morning I'd have it off. So if anybody looked up at the third floor balcony, they would see no antennas. So there is a way to have fun with these antennas for locations that we're forced to live in sometimes.
All right, so what we're going to do here real quick is show you, let's assume you can put about in your townhouse, you don't want to get the Outbacker, you want to do something really cheap. Let's assume you can drop a wire down and feed it at the base. This is just with a single ground wire. So what happens is I have one 30-foot ground wire, a 30-foot vertical wire. What do I get? So we're trying to do this on 80 meters, which is a pretty lousy antenna for 80. And you can see it's pretty lossy because our ground losses are very, very high. We have, our radiation, our feed point impedance is about 28 ohms, but we've got about, minus, 1,200 or so reactance to tune out. But again, it doesn't really work that well for us. So same thing on 40 meters, a little bit better. Again, this is one of the simplest things we could put up wire-wise. Again, you can see the pattern's not all that great. We're losing a lot of power in the ground. Feed point impedance is not bad. It's like, 50, 60 ohms and only minus J150. So your tuner and your radio could probably actually tune it to this band, but you're not going to get out that well with this kind of antenna. And I tried the whole thing here on 20 meters. It's better, still not great. And our feed point impedance here, again, it says it's now basically end-fed halfway vertical or close to it is very high. And you can see we're talking about somewhere between 3,000 and 4,000 ohms feed point impedance. So that's probably not a good idea. So how about using a rain gutter? Okay, if you're in a townhouse or your HOA with a 2-story house, 3-story house, if you have a plastic rain gutter, put wires inside the rain gutter. If you have a metal gutter, make sure all your sections are connected securely and electrically. And then let's install a ground rod at the base by your rain gutter, or you can run some radials if you can to hide them out from view around under the mulch. Now let's feed the antenna between the rain gutter and your ground. So I did that. So we got a lot better here than we were before. It's not as great, but it still works pretty well. This is on 40 meters. There's no radials. Again, we just stuck a ground rod in. You can see here, again, we have a fairly high feed point impedance. It's about 350 minus J, 260 or so. But, it's not too bad of a pattern. It's not great for this. But let's try this on 20 meters. Well, 20 meters starts looking pretty decent. We've got, net gain, max gain better than isotropic. Our feed point impedance is like 120 ohms minus J 500, 550, something like that. And the actual pattern looks pretty decent. So here's our hidden rain gutter antenna on 20 meters. Let me take it up on 15 meters. Our pattern is actually looking better, except, of course, because of the heights, we've got the vertical pattern, but overall, the pattern is not bad. Our feed point impedance, again, is pretty high. We're running around close to, you can see here, about 1,800 ohms total feed point impedance. So again, we need a NFET, but actually it's an antenna that could work reasonably well, as you can see here on 15 meters. And I tried it also on 10 meters, and our pattern looks pretty decent. All in all, it would get out pretty well on 10 meters. And again, the feed point is a little bit on the high side because of the length of the wire is relatively long to a wavelength. So you can see here we're around 500 ohms minus J450. So this is what you could do basically by hiding some wires in your rain gutter, to give you an idea. So one of the things we've talked about is short antennas are kind of hard to deal with. If they're relatively small with regard to a wavelength, you have a high reactance. Typically, we've got the low feed point impedance to deal with. So can you make your wires look electrically longer? And the answer is yes. Commonly, one of the things they do is we add inductance into the wire that is basically a coil wire. And you'll find that on all the buddy pole antennas. And also most all the mobile antennas use some sort of a loading coil to basically make the antenna look electrically longer than it is physically. There are losses, and that's just part of the trade-off. The other thing we can do is add a capacitive hat to the end of the wires to make it look longer. That basically this is wires that we put at the end of the wire, at your antenna wire, at right angles that extend down. They can actually be disc or just random pieces of wire hanging out, but basically they also make it look. So kind of summarizing here real quickly, if we're doing this really space constraint, you can use the HF 6 meter, whatever whips. They can't whip off your balcony, but make sure you've got some metal behind it, either the balcony railings metal. If it's not, then put some wires, get some screening, metal knit mesh, chicken wire, whatever, on the backside. And or you can actually put two of these mobile antennas together, just like the buddy pole is, and operate those as a dipole. And I'm sure you can go online to see people doing that, where they take two Hustler whips and mount them back to back. You do lose efficiency. The coils are going to dissipate some energy, so they're going to be lower efficiency than your wire antenna, but you can get out with them. So let's talk kind of summary in general here. As I said, any length of wire is going to radiate and receive energy. Okay, the question is how well, and also consider your losses in your ground and the conductors. And what direction the energy goes in depends on what you want to do with your antenna. At lower frequencies, as we've shown, a lot of the energy goes toward the zenith, and this is actually useful at low frequencies for what we call near vertical incidence. Where basically the energy that's reflected, that is directed at an acute angle toward the ionosphere, will actually bounce back. So for short range, without to a couple hundred miles, it works well. Yet at frequencies up above about 8 megahertz, you're just radiating your energy into outer space at the high angles, because that energy does not bounce back at those angles and those frequencies. So the ionosphere is very frequency dependent in terms of what angles of incidence it'll return energy at. There is no perfect antenna for all applications. They just don't exist. Every antenna has a performance trade-off, and what's good for a DX is not necessarily a very good antenna for your local traffic nets. I remember being told years ago that the University of Pennsylvania, for example, actually had a Yagi on 80 meters, 2-element Yagi, but it was pointing directly up. So it was only there for doing the local traffic, statewide traffic. It wasn't there to talk to anybody more than, 200 or 300 miles away. And for anywhere you can get up, the reality is the challenge is matching that feed point impedance to your equipment and avoid your gear being part of the antenna. That's kind of the bottom line here. And also, although sometimes we can get by with broadband transformers, be prepared to retune your matching network when changing bands. Best way to do this is buy one of the modern antenna analyzers, MFJ, whatever. Hook it up to your antenna, your input port to your tuner, and then adjust your tuner for minimum VISWAR, and then connect your rig up and tune it up. Generally speaking, for a lot of the antennas that we've shown, the built-in tuner of the radio just will not hack it most of the time. There's only if your impedance VISWAR is fairly low, meaning typically 5-to-1, 6-to-1, or whatever, or less, is that tuner going to work? Otherwise, it will not be able to match the load. So let's talk about small transmitting loops real quick. This is kind of another good option. Typically, they have a very high Q. That means they're very reactive. So they need to be retuned even for relatively small changes in your operating frequency. Typically, if you move 25 to 50 kilohertz on HF, you're going to have to retune that loop antenna. They have very low radiation resistance, so losses in the conductors do impact efficiency. So it's important to get loop antennas that have very low losses, resistive losses. We also had very high RF circulating currents, which is another reason we need very low resistance conductors. And we also have a great deal of very high RF voltage across the open circuit where the tuning capacitor is. So for high power, you need to be very careful of your voltage and current ratings on these things, because we really can get some very high voltages. And so we got to be very careful with these antennas. But they are small. They can fit on your backyard deck. They can go on the balcony. You can actually even probably sit them in a room. So there's a good place for them, and they're a good option if you're really constrained. So what will work for you? Let's talk about it. So the good news is we're coming up on solar cycle 25. So operation on the higher frequencies is getting better and better, and will get better, hopefully, as the next few years, which means that you'll be able to get on 15, 10, 20 meters and pretty much work the world 24/7 eventually, with the sunspots cycle going up. So the good news is that the shorter, smaller antennas will let you actually get on the air and actually make a lot of contacts. So unlike, trying to have at the bottom of the sunspot cycle where we're trying to slug through using 80 and 40 meters, the higher frequencies open mean that basically you can get by with a lot smaller antennas, which are a lot more practical. Oops. So if you're in an apartment, you're in a condo, a high rise, you have no place to really put wires. Okay, so go look and put in the small transmit loop on your balcony like we just talked about. Go get a pair of mobile whips or buy a buddy pole and use those as a dipole. Or just cant a mobile whip like Ron did off the balcony. Run as much wire as you can behind it to act as a counterpoise, and get on the air with that. And Again, with our change in the sunspot and operating at the higher frequency, that always works much better than it does on the lower frequency. So you can. As a last resort, okay, you can attach a wire to an outside ceiling or wall and make a wire antenna. If you're on a townhouse, your HOA, restricted dwellings, let's go. You can do a concealed antenna. We talked about the rain gutter. People have talked about, you've seen flagpole antennas in QST. You can use a portable antenna like Ron just showed you, a vertical half-wave whip or mobile whip with wire counterpulleys. You can do a small transmit loop antenna on your deck also. Invisible antennas, such as we were talking about, so take a small black gauge black wire, run it to a tree. Nobody's going to see it, probably. And feed it with a good antenna matching. Some people put antennas in their attics, such as dipoles and large loops. Again, this all works, but be careful. So here's one of the problems and concerns we have with some of these ideas where we're really putting antennas close to our living spaces. First of all, your antenna is close to your house, is close to your wiring, is close to your neighbor's wiring. Your antenna is going to induce RF currents in all the wiring around it. Okay, this is going to impact your antenna characteristics because your real antenna is, again, all that by wire that it couples into, and that's going to re-radiate energy. So the pattern is going to be kind of weird. You have the potential to cause interference to people's stereos, telephones, their TVs, LED lighting, and whatnot. I recall when I was very young, I had built a kilowatt linear when I got out of college. I had in the basement of my parents' house. I had a 20-meter quarter wave up on a vent pipe with radials. But if I got one at that kilowatt, I could actually cause the hall light bulb to, dimly come on and off and flicker with my modulation. So, you're going to get RF into it, all the wiring. So on receiving, this can also be a problem because your antenna is going to couple a lot of noise from the house wiring, from appliances, especially those nasty switching power supplies that are used on everything these days, from the LED lights to the wall warts for whatever. Switching power supplies are kind of the standard today, and quite often they're not, I think, do not necessarily always meet the FCC requirements, even though they're supposed to. So that's another issue we're going to have to deal with. So you may not be able to hear some of the weak signals on HF because you're going to be masked by the noise, but that's, again, one of the trade-offs. You can look at having lower noise antennas, or we would recommend particularly loop antennas tend to be more immune to picking up noise. So you may need to invest in a separate receive loop antenna just to deal with the noise issue so you can get a good signal-to-noise ratio. It's more important, and particularly at HF, the signal-to-noise is more important than the gain of the antenna. So even if you have a lossy antenna, if it picks up the signal better than it picks up the noise, you're ahead of the game. So I'm going to talk real quick about RF radiation hazards. This is the last part of our presentation. There are, in the rules and regs from the FCC, there are RF field exposure limits on all RF transmitting devices. This includes the amateur radio service, and the rules have been relatively recently tightened a little bit, okay? First of all, for rad hazards, there's really two sets of criteria. There's a set A for persons who are aware of their exposure to RF, which generally would apply to you and maybe your immediate family, and one to the general public who are not aware of the exposure. This would apply to your neighbors, okay, the folks next door, above and below. So you got to be a little bit careful here. At HF, these limits are based on E field and H field maximum levels, and they are frequency dependent. And you're allowed a much higher exposure levels on 160 meters than 10 meters. So as a matter of fact, about 20 dB difference between the two frequencies. And you are required by the FCC to evaluate your station's compliance with meeting these RADHAZ limits. and that's in the rules and regs. You can go read it online if you want. So what is the limits? Well, this chart is the current limits that apply. This is derived from an IEEE standard. And as you can see here, the electric field strength for the case of you who are aware of your RF at 160 meters is 614 volts per meter, drops down to about 61.4 volts per meter at the top of 10 meters. For the general public, it's a lot lower value, and you can see here at 10 meters, at the top of 10 meters is only 27.5, not 61.4 volts per meter. We also have the magnetic field strength. So if you're running a loop antenna, typically the magnetic field strength would dominate over the electric field strength, whereas electric is probably dominant over the magnetic for your wire antenna, your dipole type antennas. Real quick comment here, if you look at the equivalent power density, the electric field strength is a little bit more stringent than the magnetic one. And that's because of their studies they've done over the years say that you're a much better leaky antenna for vertically polarized waves, electric waves, than you are for magnetic waves. The other difference in the criteria is the averaging time. This exposure limit is averaged over a period. In the case of your occupational, we call it controlled exposures, it's 6 minutes. So you have a 6-minute interval over which you average the field levels to see if they exceed this standard. For the general exposure, you have a 30-minute exposure. So for short QSOs, you might actually get by a little bit because you're not on the air. Again, there's a time factor that gets into this because it's a time averaged value, not just an absolute max value. Okay, so what does this really all mean to you? So at HF, I said they were based on E and H field levels, not power density. Recall that I was talking about the fact that around the dipoles, we have 2 E fields and 1 H field. And the radio, quote, reactive field, while it does not retain that energy and it falls off as 1 over d square, does contribute to the hazard level near the antenna, for radiation hazards. Okay. The same thing is true of a loop. We have 2 H fields, and while only one of the H fields contribute to the radiate power, both contribute to the hazard level near the antenna. So what does that mean? Well, if we try to compute the distance away from the antenna at which we exceed the rad-haz limit, we can simply take the power times the gain of the antenna, divide that by 4 pi d squared, which is basically the formula for the area of a sphere, which is you think of your energy ballooning out, and calculate the power density. And using 377 ohms for E and H, we can calculate the E and H field levels that would exist for that power density. The problem is this does not consider those near reactive fields. So when we try to calculate out our distance from the antenna that we might exceed the limits, we can't just base it on the power. We have to think about these reactive fields. So how do we do that? So in my case, I got one of my antennas in trees in the backyard. They're at least 20 feet or more above the ground. And I really don't have any hazard issues. But if you have antennas in your room, on your balcony, in the attic, or close to the house, you potentially can exceed these exposure levels even at 100 watts, okay? QRP, you're probably good. Running 5 watts, you're probably good. And as I said, because the criteria is frequency dependent, the worst cases can often be at 10, 12, and 15 meters rather than the lower frequencies, because the criteria is the tightest there. And as we mentioned earlier, it's a little less stringent for H field than E fields when compared to the equivalent power density. So how to determine if you have a hazard, okay? The best way to do it is to have rad-haz meter made by Norda or something like that. Unfortunately, they cost more than your radio equipment, probably. They also need to be calibrated every 2 years, and the calibration cost is almost as much as the meters. It's like about $6,000 to get a set of rad-haz probes calibrated every 2 years. So that's not really a viable thing unless the club wants to invest in buying a set of them for everyone to use and spread the cost. Antenna modeling is a good way to go. We can use NEC or Easy NEC. But the problem, again, is it's easy to do with free space, but not in your house. Because, again, we have the house wiring, and all that can affect, to some degree, your antennas. So we got to be a little bit careful about how we model and what we model. Overall, rad-haz is another topic we really need to go over in the future, and that's really a much larger presentation that we need to do. So we'll work on that. So that's about it for here.
Excellent. Well, so Lee, Ron, you guys put a ton of effort into this presentation, and you took a topic that is enormously complex and often way more controversial than it ought to be, and made it pretty straightforward. I think I learned a lot, and I really appreciate it. So bravo Zulu, guys. Thanks very much for the great presentation.